All right, this worksheet number 11, we'll talk about independent events and multiplication rule for probability. So one of the main point of today is independent events. It's basically we're looking at two events and see if one event is affecting the other event. So like, are you a type of person who get affected by the weather? Suppose that Cindy and Carrie both usually have 80% chance of passing an exam, right? So suppose that. For Cindy, if it rains on the exam date, it goes down to only 75. So maybe she gets affected by the weather, so she actually had lower chance of passing the exam when it rains. In that case, the chance of passing an exam is affected by the weather, right? For let's say Karina, even if it rains on that exam date, the probability remains at 80%. So for Karina, it doesn't matter if it rains or not. She still has 80% chance of passing an exam. So for her, the weather doesn't affect the chance of passing the exam. So for Karina, passing an exam and the fact that it's raining outside, they are independent events. So this is the concept of independent events. In this worksheet, we'll investigate the property of the independent events and multi-stage experiment. So more formally, what does it mean that event A and event B are independent? So here we're now talking about two different events and how they are related. So here I want you to have a conceptual understanding of what independent events mean and also be able to verify it mathematically. So first, conceptual understanding. If the probability of A occurring is not affected by event B, then A and B are independent events. Just like Karina, where her probability of passing an exam was not affected by the rain. So in that case, we're going to say they are independent events. How do I mathematically show that? Mathematical verification. To mathematically show two events A and B are independent, we need to show one of the following is true. So basically, we try to translate conceptual understanding into mathematical statement. So first thing is probability of A given B is equal to probability of A. So imagine probability of passing basically is equal to probability of passing given that it's rain, right? So conditional probability, that little bar thing means is given or is provided. So even if it rains, probability of passing is exactly the same as just probability of passing normally. If that's the case, then we're saying they're independent, right? So this part is just mathematical translation of the conceptual understanding. Another way to look at it is the second one is kind of used less frequently than the first one. It's probability of A times probability of B. So if the above formula is not true, then the event A and event B are independent. I mean dependent, not independent, that means it's dependent. So for our first example, Cindy, probability of A was 80%, but probability of A given B was only 75%. So those two numbers were not the same. So for her, those two events are dependent events. All right, let's look at the series of questions here. Let's look at number 1. Determine whether two given events are independent. Part A, when a die is rolled twice, the first roll is even number and the second roll is also even number. So I can kind of think of it this way. Let's call this the first roll. I'm going to call that B. I know, kind of weird. Why am I calling it B and A? It doesn't matter, but I think it makes more sense in this case. Second roll, even number, I'm going to call that an A. So probability of second one roll is even. I want to compare that to probability of second is even given the first one is even. I'm basically using the first equation, or first formula. So probability of second roll is even, well, it's like 3 out of 6, right? Let's look at this part. Probability the second roll is even, given the first one is even. Like, what does it even matter what happened on the first roll? Second roll, I still have 3 over 6 probability, so this is also 3 over 6. Hey, these two numbers are exactly the same, so independent, right? Meaning it doesn't matter what happened on your first roll, but probably getting even on the second roll is still 3/6. That's why those two events are independent events. All right, let's look at part B. When testing for a virus, having a virus and tested positive. I feel like if you have a virus, probability that you're going to be reacting positive is way higher than if you don't, right? So I feel like this is the probability of tested positive versus tested positive given that you actually have a virus is going to be significantly different. So here, probability of tested positive versus probability of tested positive given that you have a virus. I feel like the second probability is way higher, right? I mean, say I don't have a number, but here, this is conceptual question. This probability should be way higher if the test is somewhat accurate or somewhat reliable, because if you have a virus, that's why you're supposed to test, right? So in this case, I feel like, oh, this is not independent, so dependent. All right, I'm gonna have you try C and D. Let's look at part E. Nick is a semi-professional dart player. Normally he has 35 chance of making a bullseye. However, when he's a little drunk, the probability goes down to 28% again. Oh, so probability changed. So that means they're not independent, because independent means the probability stays the same. So probability of making a bullseye versus probability of making a bullseye given drunk. So this is 35%, this is 28%, not equal, so dependent. If there's a player who has 35% without getting drunk, still 35% with getting drunk, then for this person, those two events are independent, means like being drunk does not affect your performance. So in that case, is independent. Here, it was not the case for Nick. So again, we have to look at the number to figure out those two events are independent or not. Here I'm going to be pause, complete part C and part D, and then we'll meet back at a multi-stage experiment. All right. In the previous worksheets, we mainly looked at probability of an event resulting from a single stage experiment. Single stage experiment just means that we're selecting one item, or experiment is done only once. So for example, we select a single card. We roll a die once. We selected one person, and etc. But what if the experiment is repeated multiple times, or something happens more than once? So we'll look at the more interesting case where things are happening more than once. So a multi-stage experiment is when experiment is repeated multiple times. Hence multi-stage, multiple times. We are selecting now 2 cards or 5 cards. So I select the card, then I select it again, and I select another card, and so on and so forth. Now experiment is repeated a bunch of times. Rolling a die twice or rolling 2 dice, selecting 25 people for a survey. So these are cases where I'm gonna do a certain experiment multiple times. So this is called multi-stage experiment, which is more realistic. Also, it can refer to the case where multiple experiments are being conducted. You know, rolling a die and flip a coin, something like that. So what happens when we have a multi-stage experiment? So for a multi-stage experiment, the probability of getting A on the first experiment, it's the first trial. Sometimes I'm going to refer to it as a trial. And getting B on the second experiment or trial. So again, multi-stage means I'm doing it more than once, or I'm doing it multiple times. So let's look at the simplest case when you have 2 cases. So I'm rolling a die twice, I'm selecting 2 cards, I'm surveying 2 people, right? So the probability of getting A on the first trial and then getting B on the second trial is given by, so it's probability of A and B. Again, we're using this A and B, the intersection, but slightly different way because it's multi-stage, is probability of A times probability of B given A. So as I mentioned, this refers to the first experiment, and B refers to the second experiment. But given the first thing, the outcome of the first experiment is already given. So it's P of A times P of B given A. All right. This is called the multiplication rule. I'm going to highlight multiplication because we are calculating the first probability, then we're calculating the second probability, then I'm multiplying it. That little dot means multiplication. So basically, I'll calculate each probability separately, then I'll multiply them together to get final answer. All right, let's look at some questions here. Number 2, a card or cards are selected from deck of cards. Answer each question. Remember, for a single stage experiment, that means when you want only one item selected, we don't really have to use the multiplication rule. So just let's keep that in mind. Because sometimes we'll just try to use multiplication rule all the time, but if you're just selecting one item, then I don't need to use that. I can just count and then that's it. So part A, it says, when one card is selected, what's the probability that we get diamond and red? Again, this question can be slightly misleading because it's diamond and red. But here I'm selecting one card, right? So I don't need to use multiplication rule. Here I just have to imagine the deck of cards is diamond and red, so I just have to look at the cards that are diamond and red. So well, diamond is red, so there are actually 13 cards out of 52, right? So that answer will be 13 out of 52. Let's look at a more interesting question, part B. When 2 cards are selected, so here already I noticed that this is going to be multi-staged because multiple items are selected. So that means you're picking the first card and you're picking the second card. So I'm experimenting twice. What's the probability that first one is diamond and second one is red? Okay, so this is a perfect time to use my multiplication rule. First event is going to be my A, second event is going to be my B. So according to the formula, this is going to be, let me write it underneath, probability of A times probability of B given A. So probability A, I'm just looking at the first event that I get diamond. Well, there are 13 diamonds again out of 52 times. And then the second part of the multiplication rule is probability B given A. So in this case, B is getting a red given the first one is diamond. So, well, okay, first one was diamond, so that card is gone for the second card. So first of all, I have only 51 cards left. So for second part, I'm gonna have it's gonna be out of 51. Now again, diamond is red, one of the red cards. So diamond is gone. There are 26 red cards. So for the second card, I only have 25 red cards left. So second part of the formula is 25 over 51. So my final answer is 13 over 52 times 25 times over 51. For probability questions, you can just leave your answer as it is. You don't have to calculate it to decimal or anything. It's better that you just leave it as an unsimplified fraction. All right, let's try one more together and then I'm going to have you finish the rest of it. Let's look at part E. It says when 2 cards are selected, what is the probability that both cards are red? Okay, so what does this mean? Both cards are red? I have to translate like this. Means first one is red and second one is red. So some of the questions I have to like translate what the question is saying into like something A and B. So they say both cards are red. That just means the first one is red and the second one is red. So first red card is A, second red card is B. So kind of same thing. Probability of A times probability of B given A. So probability of red on the first one, that's A. So there are 26 red cards out of 52 total cards. Again, for the second one, because first one was red, one of the red is gone. So I only have 25 left out of total 51 cards now because, again, one card is gone. So 25 over 51. So that's my answer. Again, I'm going to leave it as it is. Okay, I'm going to have you pause and now finish the rest of number 2. Remember, some question we're only selecting one card. Some question we're selecting multiple cards. So I just want to make sure that you know the difference. So why don't you pause a little bit and finish the rest of number 2. All right, once you're done with number 2, let's go on to the next part. So there is a formula that will help us calculate P, A, or B. Notice that now we're not talking about A and B anymore. Now we're talking about A or B. So this is a slightly different formula that we're going to talk about when we can't directly count the cardinality of A or B. Again, cardinality just means like how many things are in it, right? Usually I can just count how many things are in A or B, but sometimes information is not given, so we have to use, this formula will be able to calculate A or B. So this is A, probability of B, so it would be probability of A plus probability of B minus probability of A and B, which is the intersection part. Again, this is union part and this is exclusion part. As I mentioned before, if you can directly calculate the cardinality of A or B, then you don't even need this formula. All right, so here we have a contingency table again, or frequency table. Then bunch of ticket, people who got ticket, people who didn't get ticket with different color of a car, right? So here, I think the common belief is that if you have a red car, you're more likely to get a ticket. So here they'll try to see the data to see if that's actually the case or not. So here we have a bunch of different probability question. Again, this kind of question, reading the question carefully is kind of key because every question is going to sound very similar. So if we look at part A, one person is selected, ticket and red. I'm going to highlight. If I look at, I'm just going to scan through each question. Part B, it says ticket and there's a bar, so that's conditional probability, ticket given red for part B. And part C is red or not red, right? So there's an and question, there's a conditional probability question, and then there's an or question. And then part D is like 2 people. Oh, so that's a multi-stage question. So there could be and question, conditional probability question, or there's a multi-stage question. So let's look at part A. It says one person is selected, ticket and red. So I'm looking at these groups. There's a ticket intersection with red. So basically you have to have a red car and you got ticket. So that'll be just 24. Actually, what I forgot to do is we should just tally up each column and each row to make it a little bit easier. So if you look at all the people who got ticket, that'd be 24 plus 49, so that'd be 73. People who didn't get any ticket, that's 134. And then people who have red car, 60, 72. And then people who do not have red car, that's 135. The total of 702, 207. All right, so let's look at ticket and red. So those are the ones that have tickets and they have red cars. So that'd be that 24 people out of total of 207. Look at the second question. If one person is selected, find the probability of ticket given red. Okay, given means it's only out of people who have red car. So second part is the given part. Again, this is where your sample space changes. So it'll be out of 72. That's everyone who has red car. So out of those 72, how many people got a ticket? That'd be 24. So I want to make sure you guys know the difference between part A and part B. Part B, we have a denominator is not total number of 207 anymore because of its conditional probability. Part C, it says one person is randomly selected. Find the probability that is red or not red. Oh, that's a tricky question. Red or not red. So this is a union, combines everyone. So everyone has a red car. Also combine that with people who have not red car. So that's everyone, 72 and then 135. So this is a tricky question because this refers to basically everyone. So, okay, 207, that's just 207 over 207. That's 100%, or 1, right? Let's do one more, or a few more. If 2 people are selected, what's the probability that they both have a red car? Okay, so in my head, I'm going to be using multi-stage multiplication rule. It says, again, both red car. That means the first car is red. So I'm going to rewrite it as like first is red and second is red. So that's like my A, this is like my B. So probability of A times probability of B given A. So probability that first car is red is 72 There's 72 red car out of 207 times. So probability the second car is red given the first one is red. So okay, so now there are 71 cars are left, red cars are left out of total of 206 because I already picked one red car. So my final answer is 72 over 207 times 71 over 207. All right, let's look at part F. Are two events, ticket and red, so red car and ticket, independent events. Calculate the appropriate probability to support the answer. So back when we talk about concept of independence, so basically it's like color of your car does it influence if you're more likely to get ticket or not. So mathematically we have to show probability of A given B is probability of A, right? So ticket is like A, red is like B. So probability of A given B, is it equal to probability of A by itself? So probability A given B, we calculated that. Ticket, given that you have a red car, it was 24 out of 72. I'm getting answer from part B. So that was the previous question. Probability of A by itself, probability that you get a ticket, so that will be 73 out of 207. So 73 out of 207. So are these two numbers exactly the same or not? So let's calculate. So this is the time where I have to actually want to put it as a decimal to see if they're equal or not. So if I calculate 24 over 72, I get 0.333. On the other hand, if I look at probability A by itself, I get 0.353. So they're similar, but they're not exactly the same. So the answer is no, they're not independent. Independent. Because those two probabilities are not the same. All right, I'm gonna have you finish the rest of the number 3, and I think that's it for this worksheet.